which a periodic internal, entrainment is the process by which a periodic repetition of some external cycle, light, dark, temperature, causes a circadian rhythm, which is internal, to remain synchronized with that external cycle. All right, so the external environmental cycle entrains the internal circadian rhythm and causes it to be synchronized, because that's in the plant's best interest, to be synchronized with the external cycle. Okay, so entrainment is a big deal. Okay, here's a really cool example. This isn't a plant example, this is a plankton example, a protista example. So Goniaulux is a marine algae, and there are 3 different functions that follow separate circadian rhythms. All right, they're peaking at different times of the day. Bioluminescence peaks in the middle of the night. That's a good time for your glow in the dark to peak, right, in the middle of the night. Photosynthesis peaks in the middle of the day. It's a good time for that. Cell division is restricted to just the hour, a few hours just before dawn. I don't know why that makes sense. I'm not sure. The other two make sense. But here's the thing: if Goniaulux is kept in under constant environmental conditions, basically you cut off its access to its external cues, these functions continue with the same rhythm for days. Okay, so that kind of proves that it's internal, but how do we know that those internal rhythms are synchronized by the environment? Because we can change them. We can change the circadian rhythms by changing the environmental cues. We can change those natural internal rhythms and get them to peak at different times by changing the environmental cues. Okay, so look at this. Normally these phytoplankton are going to be peaking every 24 hours, right? A 24-hour day. It'll be peaking at noon every day, all right? So every 24 hours it'll peak again, and then peak again. But if you change the daylight cycle to where it's only 6 hours of light and 6 hours of dark instead of 12 and 12, which would be normal, right? You're going to get that those algae to peak every 12 hours instead of every 24. That's a really severe change. Okay, but it shows how much these internal rhythms can be entrained by the environment. But the cool thing is, if you then take those organisms and place them back in constant dim light, you don't give them access to the cues anymore. You know what they go back to? They go back to the regular 24-hour rhythm. See, that's amazing. They go back to their default state. That's right. So normal every day, bioluminescence peaks at midnight, and then valleys at noon and peaks at midnight. That's 24 hours, right? You change it to 6 hours of light, 6 hours of dark. Every 12 hours it peaks, right? So it's artificial. You couldn't say midnight or noon. It just peaks every 12 hours instead of every 24. But you shove it back in a closet, constant dim light, it goes back to the 24-hour cycle. That's pretty amazing. So that actually shows a lot of stuff. That shows that the rhythm is truly internal, but it also shows the power of entrainment. So those things are working hand in hand, endogenous rhythms and entrainment by the environment. Okay, this is just a picture of that. This just shows you photosynthesis peaking at noon, bioluminescence peaking at midnight, and kind of showing you that they're on these 24-hour rhythms. Here we have somebody changed the daylight now to 6 light, 6 dark, 6 light, 6 dark, and we've changed the peaks now every 12 hours. And then we return them to constantly dim light here, right? Boom, back to the 24-hour cycle, almost immediately. Okay, so there's an example of the biological clock, right? These endogenous circadian rhythms, right? Exerting control or coordinating daily events. Those were all daily events, weren't they? Those were all daily events. Circadian rhythms by nature are daily events, 24-hour cycles. But if you think about it, it's not a stretch to think that some of the same mechanisms are helping to control seasonal events for plants. Right? Plants they're cueing in sunlight and temperature, right, to be able to know when it's day, when it's night. It's not a stretch for them to be monitoring the same things to tell when it's summer, when it's fall, when it's spring, when it's winter. They're monitoring the same kinds of things. And the key there is not only does the temperature get cooler as we go from summer into fall, but the days get shorter. Plants are really good at measuring daylight, right? You can imagine that. And so, in addition to coordinating daily events, biological clocks are enabling plants to respond to changing seasons by accurately measuring changing day length. Plants are measuring day length. How many hours of sunlight are there today? Because that gives me some information as to the season. That's amazing. In fact, if you think about it, measuring day length would be more accurate than would be to measure temperature. Right? Because right now, November should not be this cold. Sort of if you were to look at 30-year climate patterns in Virginia. It's colder, it's unseasonably cold. But the day length is the same as it's always been this time in November. So it's a little bit better to do that. Even in the tropics, right, where days are pretty much the same length all year round, they're long all the time, plants are sensitive to very, very minor fluctuations in daylight. And so plants are using their monitoring to synchronize flowering with seasonal events such as wet and dry periods. Plants gotta do certain things at certain times based on what's coming seasonally. Right? In a place like Virginia, it's more, temperature, day length, but in the tropics, it's wet and dry seasons, right? Some places are wet and dry seasons. And those can be correlated by some of these day length events as well. Okay, and so photoperiodism then is a biological response to a change in the proportions of light and dark in a 24-hour daily cycle. So circadian rhythms, or these 24-hour cycles, photoperiodism is a plant's tendency to respond in some way based on changing day length. That would be a simple way to say it. So photoperiodism is dealing with seasonal responses of plants. Check this out. Some plants will only flower under certain day length conditions. Many plants are what we call photoperiodic. That means they're measuring day length to see when they should flower. They're photoperiodic. Not all plants are like that. Some plants ignore the sun when it comes to when they should flower. They're cueing in on other things. So for example, tobacco and soybeans are what we call short day plants. They will not flower unless the day length is shorter than some critical number of hours. They're short day plants. All right? And we're going to talk about short day and long day plants. It doesn't mean that all short day plants flower on what you would think of as a short day. It just means they're looking for some amount of time less than some critical mark. So shorter than this amount of time. Whereas long day plants are going to flower when there's this amount of sunlight or more. That's what long day means. Look, animals are doing the same thing. Animals are photoperiodic too. They're measuring the length of the days and they're adjusting their mating behaviors accordingly. Okay? So this is well studied. So again, short day plants have to have a light period shorter than some critical length in order to flower. So that's the definition. Shorter than a certain critical length. Now, it turns out that short day plants are also typically flowering on short days. So they're typically flowering in the early spring or the fall. Okay? But theoretically, you could have a really long day that they're flowering on as long as it's less than a certain critical long period. Right? But it turns out that they do tend to flower on short days. So common cocklebur, here's an example of what I'm talking about, will flower by 16 hours of light or less. 16 hours of light, that's a pretty long day, if you think about it. 16 hours of light and 8 hours of dark, that's a long day. But cocklebur will flower with 16 hours of light or less. That's why it's a short day. Mums, poinsettias, strawberries, primroses are all short day plants. Long day plants, on the other hand, must have a certain light period that's longer than some critical amount of time. So they'll flower with this amount of sunlight or more. All right, they typically flower in the summer. Spinach, potatoes, wheat, lettuce, henbane are all long day plants. And then, like I mentioned before, some plants are day neutral plants,